All right, so I don't have too many goals for today, although it is going to be a little bit of, we're going to have a conversation about solutions. I know we've talked about solutions already. So there's going to be quite a bit of stuff that goes on with this. And well, it's in this next section can definitely be a little bit confusing. So be sure to kind of keep up with me on this one and do some practice problems when it comes along. What we're going to talk about is molarity. And molarity is a weird word, and the reason that it's a weird word and a confusing concept is because it sounds a lot like moles. So remember, we had moles and molecules. We were asking questions about moles and molecules. And I said, when we introduced moles, I said, well, moles sounds confusing, or it can be confusing because it sounds like the word molecules, and people might get confused between the word mole and molecules, particularly because I ask you questions about molecules and I ask you questions about moles. Well, now we're introducing another word that starts with the letters M-O-L, and that's molarity. And so again, it's not molecules, it's not moles, it's molarity, but it does sort of involve moles. And we're going to talk about moles goes into the definition. And so we'll get into that here in just a second. This is a conversation about solutions, and molarity is a unit of concentration for solutions, just like percent by volume or percent by mass, or density is sort of a unit of concentration in its own right. And we're also then going to parlay that into a discussion about electrolytes and a discussion about pH. And so in this class, you're not going to do a lot of pH calculations, but we do need to define it, and we need to understand what it means. And so let's go ahead and get started, because we need to get going with solutions, and we'll start off with electrolytes, and then we'll define molarity. So let's do that. All right, so let's say we have a solution. And we've already talked about solutions in the sense of whether or not, we've talked about solutions in the sense that we've defined them as homogeneous mixtures. So we know that it is a mixture, and we know that it is also homogeneous. But what we want to do is we want to express how much of a solute is in the solution. And let's just make sure that we've talked about this. There's two components to a solution. There's the solvent, and there's the solute. When it comes to a solution, the solvent has to be a liquid. And the reason it has to be a liquid is because solutions are liquid in their state. So in order to have something that's a liquid in its state, the major component has to be a liquid. And I said it before, I just said it. Not only does it have to be a liquid, it has to be the component in the largest quantity. Okay. So the solvent it's what does the dissolving. So when I'm talking about a solution, I'm going to put something into the solvent, and that's going to dissolve, solvate the solute, or whatever I put into it. The solute is It's what gets dissolved. It's in the smallest quantity. And it can be a solid or a liquid. And it could even be a gas. Okay. It's much harder to make solutions with gases, but you can definitely do that. What's one example of a solution that has a gas in it? Does anybody remember we talked about this one? I'm going to break out my Midwestern lingo. Pop. Anybody ever drink pop? Combustion reactions produce gases, but remember, I'm talking about a solution that has a gas as a solute, or a, yeah. And so if it's, yeah, I'm talking about soda pop, soda pee. And that's what we call it in the Midwest. We call it pop. Around here, it's called soda. Well, magnesium and chloride is an ionic compound. It is a soluble ionic compound. So if you used magnesium chloride as a solute, you could make an aqueous solution. But I'm talking about specifically a gas, right? Fizzy pop soda, exactly. All right, so before we move further into this conversation about solutes, solvents, and solutions, what I want to do is I want to get a little bit more involved with what it means to be dissolved. We say this a lot, right? I mean, you say, if I make a cup of coffee and I add some sugar to it, then I'm dissolving the sugar in the coffee. But we don't actually know what it means to become dissolved. Dissolved. In terms of chemistry, what we mean by this is we're going to form a homogeneous mixture. Remember that a homogeneous mixture has a consistent composition throughout the mixture. So if I'm going to have a solute and it becomes dissolved, then in order to make a homogeneous mixture, it means to be surrounded by solvent molecules. So let's take the example of sugar. And what I'm going to do is I'm just going to draw a hexagon, because a hexagon is a very simplistic representation of a molecule of sugar. I'm going to add some groups on it. Maybe there's some OH groups. And so if I have a molecule of sugar and I have a bunch of solvent molecules, let's say the solvent is water. In this configuration, I'm not making a homogeneous mixture. The sugar is not surrounded by solvent molecules. In order to draw a correct picture of a solution, we have to draw the molecule of sugar surrounded by actual molecules of solvent. Now, at this point in our chemistry knowledge, we know that even in a very small collection of water, just say a water bottle, there are so many water molecules that the only way that we can talk about them is in terms of moles, in orders of magnitude as large as 10 to the 22nd or 10 to the 23rd. So I've only drawn one molecule of solute of sugar, and I've drawn about 6 molecules of water. And so remember that this is about as extremely blown up a view as you could possibly get. In a real solution, this is happening throughout the entire solution, such that it happens again so many times that we don't have words to describe how many times that is. We have to say all over the solution, amongst moles of water and moles of solute, this disillusionment, this being surrounded by solvent molecules is happening. So when I put some sugar into a collection of water, on a microscopic level, on a particulate level view, looking at the individual particles of the solution, we see the solvent and the solute interacting in a way that the solvent surrounds individual molecules of solute. This is how we ultimately get a homogeneous mixture, a constant composition of solvent molecules and solute molecules. And if I were to use little circles to describe, to blow up, to kind of zoom out and show this same picture, but maybe on a larger scale so that you can see a few more molecules interacting with each other. This is what it might look like using a simplistic ball model. Okay. Now, I've used sugar as an example. The formula for sugar is C6H12O6. This is a molecular compound. We could also dissolve we can also dissolve ionic compounds. What if I take sodium chloride and I make a solution out of sodium chloride? What happens with that? But remember, we already talked about whether or not an ionic compound is soluble or insoluble, and we should remember that sodium chloride is a soluble ionic compound. Now, it still becomes dissolved, so that means it's still surrounded by solvent molecules. Here's the difference. An ionic compound, when dissolved in a solution, will break up into its constituent elements. We're not quite sophisticated enough to know the actual structure of water. We will be soon. So I'm going to just continue to use this H2O picture. But I want to change it just a little bit. Because for an ionic compound, like sodium chloride, it actually breaks up into its constituent ions, and each of its constituent ions becomes dissolved. In other words, the sodium ion itself is surrounded by solvent molecules, and the chloride ion itself is surrounded by solvent molecules. So let's color code it. Let's make it green and blue. This is what it means to become an aqueous solution. So if I were to write the chemical reaction that involves the solvation of sodium chloride, I'm going to write the water over the arrow to signify, in this case, what I'm signifying is that it's not actually reacting with water. It's just, I'm making a solution. I would say that sodium ion becomes aqueous and chloride ion becomes aqueous. I think when we were talking about complete net ionic equations, we mentioned that the ions exist this way in solution. And now we're getting a little bit of a closer picture of it from the perspective of the solution itself. So this is different than if I wanted to take sugar, C6H12O6, and dissolve it in water. Remember, it's a molecular compound, so it doesn't break up. It just becomes aqueous. There is a difference between what happens with ionic compounds and molecular compounds. And so if I were to then draw this picture again with some water molecules, and then I want to add my solvent, or my solute, my sodium chloride solute, I would show the ions of the sodium being separated from the ions of the chloride. And in order to maintain the idea that it's a homogeneous mixture, I evenly distribute all of the particles throughout. Okay. Now this is an overly simplistic view. Remember that each of these particles is actually surrounded by solvent molecules. And this is what it means to become solvated when we're talking about ionic compounds. This goes directly into our next definition, which is electrolytes. When it comes to the word electrolyte, all we mean is a dissolved ion. If we think about it, electro seems to have something to do with electricity. Well, ultimately, really, it just means charge, right? So an electrolyte is a dissolved ion, a ion that has become surrounded by solvent molecules. So if we have what is an electrolyte solution? Well, it's simply a solution made with ionic compounds. And if you go to a famous energy drink, sports drink, you'll see that their marketing is centered around the fact that this sports drink has lots and lots of electrolytes to replenish your body after you've done a vigorous bit of athleticism. Well, if you look at the bottle, what are you going to see? You're going to see that it says it has things like potassium, and phosphate and sodium and chloride. It's going to talk about the ions that it has, because really when it says electrolyte, all it means is that it's a salt solution. If you wondered why your favorite sports drink tastes a little salty, it's because it's made out of salt. So this is what an electrolyte solution is. And now the last thing we want to talk about is the difference between a strong and weak electrolyte. Now, the reason why we call it electrolyte is because it will conduct electricity. This is the heart of what we mean by electrolyte solution. It's whether or not it will conduct electricity. So how does it conduct electricity? It conducts electricity because these charged particles can move around the solution. An electrical current, by definition, is the movement of charge. And if I have a charged particle in the solution that can move around, then this can conduct electricity. So in theory, pure water can't conduct electricity. So if you fill up the bathtub with completely deionized and reverse osmosis water, deionized distilled water, it doesn't have any dissolved electrolytes in it. So you can put grandma in the tub and throw the toaster in there and plug it in, and she's going to be just fine. If you get water out of the tap, because of a lot of different reasons, but primarily because the water treatment facilities add dissolved ions to the water, that does have this ability to conduct electricity because of the dissolved ions added, not only in the treatment process, but just in the process of existing in metal water pipes. It leaches some of the ions from the pipe. So you don't want to put grandma in the tub and then throw the... Yeah, kids, don't try this at home. Good point. Yeah, you don't want to put grandma in the tub and you don't want to put grandma in the tub and throw the toaster in no matter what, even if you did fill it up with distilled water. I forgot this is going to go on YouTube, and so we want to make sure that we have our disclaimer out there. Right. Kids, don't try this at home. This was a theoretical discussion. Actually, this video is not made for children. All right. So let's move on from that point. So I want to talk about strong electrolyte solutions and weak electrolyte solutions. And the words strong and weak really do refer to its ability to conduct electricity. A strong electrolyte solution is made from strong acids and soluble ionic compounds. Weak electrolytes are all other solutions. So we're not going to talk about it in this course. And in fact, we don't actually get into it until general chemistry 2. But even an insoluble ionic compound, up to this point, we just think about solubility in terms of black and white. Either it is soluble or it's not soluble. Even for an insoluble ionic compound, it does break up into some of its ions. It just doesn't do so fully. So it's not that it doesn't make any ions, it just doesn't make a lot. And because it doesn't make a lot, it only weakly conducts electricity. So insoluble ionic compounds make weak electrolyte solutions. Weak acids make weak electrolyte solutions. Strong electrolyte solutions are made from strong acids and totally soluble ionic compounds. And so that really does take care of it when it comes to defining what a solution is, thinking about the solvent and the solute and what those are, what it really means to become dissolved, surrounded by solvent molecules. And then we threw in this new word, electrolyte, but really the word electrolyte just has to do with things that we already know about, which are ions. We then added the last category, which was strong and weak electrolyte. We talked a little bit about that, what that means. Again, strong electrolyte solutions are made from strong acids and soluble ionic compounds, and weak electrolyte solutions are all other solutions, insoluble ionic compounds and weak acids. So this is really just a qualitative view of what a solution is. But in chemistry, we always want to talk about quantitative views. And so we ultimately get into this discussion about what's the concentration of the solution. Since it's a solution, we've already identified that there are solute particles in the solution surrounded by solvent molecules. But the question is how many? So if I draw this picture again, and I put some solute and have some solute particles surrounded by my solvent, then that solution has a particular concentration. If I do this again, and add a lot more solute to the solution, then the concentration has changed. In one, I have a low concentration. In the other, I have a high concentration. But more than just low and high, we want a way to actually measure the concentration. And we do that with a unit called molarity. Now, it's the symbol for molarity is big M. There's a problem with the big M because it's supposed to be italicized. The problem with drawing things on a whiteboard and italicizing is that I can't. I can try, right? Let's see. Yeah, that's not really working out, right? And so what I mean by this, what I'm trying to get at is that instead of italicizing on the whiteboard, which I can't do because nobody can draw like that. Maybe you can. Thanks, Angela. It was amazing. I'm just going to use a little underline underneath it. So I'm going to, when you see me draw it on the board, it'll look like this, but keep in mind in print that it's actually it's an italicized M. That's what that really is. So you won't see an underline underneath it in print. You'll see a capital italicized M. All right, so what is molarity? Molarity is defined as the number of moles of solute divided by the volume of the solution in liters. So it's the moles of solute divided by the volume of the solution in liters. So let's do this. You make a solution by dissolving 3.0 moles of sodium chloride in 9.2 liters of solution. What's the molarity then? Well, quite simply, it's 3.0 moles of the solute. The hard part here is that you have to be able to identify what the solvent and the solute is. Now, we'll say this is probably a water solution. And so the liters are 9.2 liters of, and I'm going to abbreviate it. I'm just going to say solution, SLN. So what is the molarity then? Get your calculators out. Do that really, really hard math. 3 divided by 9.2, and you get 0.33 molar. And this is how we say it. We say M-O-L-A-R, like the back teeth. It's a 0.33 molar solution. The molarity is 0.33. Okay, but this one was obviously an oversimplified example, right? I would say I'd actually use a little bit more complicated of an example and say something like the following. Let's see. A solution is created by dissolving 9.5 grams of sodium chloride in enough water to make 25.0 milliliters. Let's make this 9.50 milliliters of solution. What's the molarity? Okay, so the molarity is still moles of solute divided by the volume of the solution in liters. So the problem, one of the first challenges you have is identifying the solute and the solvent. Well, I think it's okay here to say pretty quickly that the sodium chloride is what's getting dissolved, and so it's got to be the solute, and that the water is going to be the solvent, and I'm going to have as much of it as I need to have a 25 milliliter solution. So now I know the volume of solution, right? It's 25 milliliters, isn't it? No, it's not, right? Because the denominator of the molarity calculation must always be in liters. And so you do have to come back and you have to use your knowledge of metric prefixes to convert milliliters to liters. And that's what you use in the denominator. The same thing goes with the 9.50 grams of sodium chloride. Sodium chloride is given to you in its mass. And so you still have to convert grams to moles in order to get the numerator. The definition of molarity is moles of solute divided by liters of solution. So we have to do this conversion as well. 9.5 grams of sodium chloride. And the molar mass is 58.44 grams of sodium chloride for 1 mole of sodium chloride. And so let me get out my calculator, 9.50 divided by 58.44. I get 0.1626 mole. And it has 3 significant digits. So 0.1626 mole of sodium chloride with 3 significant digits. Now I can calculate the molarity. The molarity is 6.50 molar. And so we would say in language, we would say the molarity of the solution is 6.50, or we would say the solution is 6.50 molar in sodium chloride. That's what we would say, in sodium chloride. And so there's definitely a lot of different ways that the chemistry department can give you masses and have you calculate moles and liters, or in other words, there's just so many different ways that you know how to convert one unit to another. We can challenge you by giving you all sorts of different ways to get moles of solute and liters of solution. We could do density, we can do grams, we can do kilograms, and even make you do 2 steps of a conversion. But at the end of the day, the molarity is quite straightforward, in a straightforward fashion. The moles of solute divided by the liters of solution. Once you know those 2 pieces of information, you can calculate the molarity. Okay, let's do one little other trick though. I do hesitate to teach students tricks, but there is a handy formula for dilutions. Now, ultimately, we can do this whole calculation with a lot more steps, but it all boils down to a little formula that every chemist uses called M1V1 equals M2V2. And at the heart of this formula, all it's saying is, if you're doing a dilution, the number of moles of solute that you dilute is the same. However many moles you dispense is going to be the number of moles in the final solution. So let's say that we have a solution that's got some solute in it, and we want to do a dilution. So we'll add a little bit of it, and then we'll fill it in with more solvent. This is what we mean by a dilution. We take some small amount of solution 1, and we create solution number 2 by adding more solvent. Now, remember, it's a homogeneous mixture, and I can't show an animation on the iPad, but then the particles that are the blue particles would then evenly spread out into the solution, and you would get a homogeneous mixture of that solution. So hopefully I'm describing adequately with words and pictures what it means to do a dilution. And so what M1V1 is saying is that whatever moles of the solvent or the solute that you take out whatever the moles of the solvent or solute that you take out of the first solution and you put into the second solution, it's the same number of moles no matter how much solvent you add to it. And so if you dilute 3.0 milliliters of a 4.5 molar hydrochloric acid solution to a final volume of 50.0 milliliters, what is the new molarity? So we can use this formula. M1 V1 equals M2 V2. Well, what is given to us? Well, we're given the molarity of the first solution. What else are we given? We're given how much of that solution in terms of volume we used. We're also given the final volume of the new solution, and we're asked to solve for the molarity of the new solution. And so we just use algebra. We're going to divide both sides by volume 2, and so we get that the new volume is molarity 1 divided by times volume 1 divided by volume 2. And so it really is just plugging things in. So what do I get for molarity 1? It's 4.5 molar. Volume 1 was 3.0 milliliters. And the final volume is 50.0 milliliters. Well, I want to stop right there and ask a question. Molarity is defined by liters of solution. Is it okay if I use milliliters, or do I have to convert it here? Is it okay? Dr. Romero says it's okay because it cancels, and that's right. Because the ratio of milliliters is the same as the ratio of liters. They equal each other. So in this case, you don't have to do any conversions. So 4.5 times 3 divided by 50, the new molarity is 0.27 molar. This is the new molarity. And so you see that I dissolved it, or that I did a dilution. I took a small amount of a concentrated solution and I diluted it in a much larger volume, and you see that the concentration went down. And so the last thing we can do is we can take molarity and we can use it to ask questions like this. We could say, how many grams of sodium chloride are in 2.95 milliliters of a 1.95 times 10 to the negative 2 molar sodium chloride solution. So it's just essentially a unit analysis problem. How many grams of sodium chloride are in this quantity? So what am I given? I'm given 2.95. I still haven't done that right. 2.95 milliliters of solution, and I'm given the molarity, 1.95 times 10 to the negative 2 molar. I'm asked for the grams of sodium chloride contained in that in those two quantity, or in that quantity of that solution. So what's the basic plan? I need to go from the units in 1 to the units in 2. Well, what unit do I start with in 1? I hope that at this point you're identifying that molarity is yet another per expression. It's a we can use it to convert between moles and volume, and vice versa, between volume and moles. And in this case, we're going to convert between milliliters and mass. But remember, that's not the full-blown plan. First of all, the molarity is given in terms of liters. So I need to use liters as the appropriate volume unit. So I need to convert milliliters to liters. But once I have liters, I can use the molarity to get the number of moles of solute. But I'm not asked for the number of moles of solute. I'm asked for the mass of the solute. So we can convert milliliters to liters, liters to moles, and then moles to grams. So putting it together, it's 2.95 milliliters of the solution. I know that 1 milliliter of the solution is 10 to the minus 3 liters of the solution. The solution was given to us as 1.95 times 10 to the negative 2. And this is where I'm going to write things out. I'm going to take the symbol, and I'm actually going to write out what it means. It means that there's that many moles of sodium chloride for every 1 liter of the solution. And then from before, we already identified that there is 1 mole of sodium chloride for every 58.44 grams of sodium chloride. And now let's follow the units. Milliliters of solution cancels with milliliters of solution. Liters of solution cancels with liters of solution. I'm now using the molarity to convert liters of solution to moles of sodium chloride. And that's ultimately going to cancel with moles of sodium chloride. And I'll be left with grams of sodium chloride. And that's what I'm looking for. So the rest is just calculator work. 2.95 times 10 to the third times 1.95 times 10 to the negative 2 times 58.44, and I get 0.0033 to the correct number of sig figs, which are 6 grams of sodium chloride. And if I wanted to put it into scientific notation, 3.36 times 10 to the negative 3 grams of sodium chloride. Okay. So what have we done up to this point? We've talked about what a solution is, made of solute and solvent. We talk about what solutes and solvents are. We just reminded ourselves about that. We talked about what it means to become dissolved, become surrounded by particles of solvent. Then we expanded that a little bit and talked about the difference about what it means to make a solution with a molecular compound and what it means to make a solution with an ionic compound. Remember that ionic compounds break up into their individual ions, and the cation and anion separately become dissolved, surrounded by solvent molecules. Then we defined then we talked about that in terms of electrolytes, weak and strong electrolytes. And then we defined quantitatively a concentration for those solutes in terms of molarity. We did a dilution. We showed you a simple formula for dilution. And we showed you some unit analysis that you can do with molarity. And that's as far as you need to be able to take molarity. Well, the last thing that I want to do is I want to talk about pH. Because pH really is about molarity. I think everybody sort of understands that pH has something to do with a measurement of acidity. Specifically, pH is equal to the negative log of the concentration of H+ ions. And if we were to think about something that's acidic, remember that HCl is a molecular compound, but when you mix it into water, it behaves as if it were ionic. It breaks up into aqueous hydrogen ions and aqueous chloride ions. And so we can measure the strength of the acid by using this measurement called pH. Now, ultimately, you don't need to do this calculation. But this is what you want to understand, is that if you have a concentration of, let's see, molarity and pH, let's make a little table. What if the molarity of the hydrogen ion, and let me make sure I do this correctly. This is the molarity of H plus ion specifically. What if it's 0.1 molar? What if it's 0.01? What if it's 0.001? What if it's 0.0001? What am I doing? Is the concentration getting smaller or is the concentration getting larger? So this one was 10 to the minus 1. This one is 10 to the minus 2. This one is 10 to the minus 3. This one is 10 to the minus 4. I'm going to stop writing them in decimal notation and start writing them like this. 10 to the minus 6. Yeah, they're definitely getting smaller, right? How does this work? pH equals 1. The pH equals 2. The pH equals 3. The pH equals 4. The pH equals 5. The pH equals 6. Let's expand this out just a little bit longer. What if it's 10 to the minus 7? What if it's 10 to the minus 8? What if it's 10 to the minus 9? 10 to the minus 10. Can you think you can see the pattern now? 7, 8, 9, 10. And you can do this in your calculator. You could actually stick in 0.01, press the log button, and then whatever answer you get, make it negative. Guess what you get? 2. Okay. And that's your pH, if this is the concentration. So what would happen if the hydrogen ion concentration is equal to 10 to the minus 13 molar? What would the pH? Is there a maximum pH? There isn't a theoretical maximum. Yeah, the pH would equal, in this case, 13. The general pH scale is, in common terms, it's 1 to 14. But there isn't a theoretical maximum. And there isn't it can even go into negative territory. Because what if the concentration is equal to 1? Yeah. Maddie, that's right. The negative log of 0.01 equals 2, not negative 2. No, ma'am. It equals 2. So if the molarity is 1, then the pH equals 0. And so what if I have the negative log of a molarity that's equal to 2? What happens then? Well, the log of the number 2 is a positive number. So if I take a positive number and I make it negative, then the pH could technically be negative. And the only thing that's limiting to you on the high side of the pH scale is, well, how meaningful is a concentration like this, right? 10 to the negative 17 molar. What does that actually mean? Well, that means that the concentration is got so many zeros in front of it that you you start to really lose the meaning there. So hopefully that sort of illustrates what I mean by that, Dr. Romero. Yeah. Okay. So what I'm going to do is I'm going to leave it there.